So far, we have considered gravity currents flowing due to continuous injection of a denser fluid in a lighter ambient. And we assume that that is continuously moving with certain speed, and that speed we try to predict using the models that we derived in the previous lecture. For instance, this particular example here, right, that gives us the velocity of a gravity current in the atmosphere, and we are assuming that there is continuous influx of gravity current, right? And likewise in a channel, for example, in this particular images, we are assuming that there is continuous injection of denser fluid, and that's why this gravity current is moving continuously. And in this case, we find that the velocity is proportional to the square root of g prime, right? And obviously h naught and other things. But what happens if we stop the influx of denser fluid after some time? In other words, let's say there is a fixed volume of denser fluid, and that fixed volume now moves from one side to the other in form of gravity current, right? So we are going to study now what happens in this particular case, fixed volume gravity current, or that is in fact same as shutdown stage of a gravity current. So once you stop injecting denser fluid, that basically makes it means that you have provided a fixed volume, and now that is allowed to flow, right? So this is an experimental example for a fixed volume gravity current, where we assume that this is the volume of dense fluid that is there at time t equal to 0. So let's say this has density of rho naught, and this has density of rho a, where rho a is just fresh water, plain water, and this green fluid is salt water. Okay, and there is a lock here, so that's a lock. And now if lock is removed at t equal to 0, right? So here this is at t equal to 0. Now if lock is removed, you see this creates a gravity current, right? This green fluid is now moving to the towards the right, and you can see that it is roughly a rectangular type shape, which we can approximate. It's not obviously exactly rectangular, but we will approximate it as rectangular. So first it was a rectangle before, now it is a rectangle of longer length and thinner depth, and then it extends further and becomes a rectangle of, again the length is increasing and depth is decreasing, right? In this case again, now depends where we define our depth, but what we see is the gravity current was thinner in length, shorter in length, and thinner in depth, but as time progresses it becomes longer and longer and thinner in depth, right? So we will try to find a solution for the gravity current motion in such cases. What happens if we release a fixed volume of dense fluid, and this does not obviously keep moving at the same speed, because its buoyancy effects decreases with time, and the speed also decreases because of its decrease in height, and as it increases in length, because indirectly when height decreases, that means its buoyancy force decreases, because we create buoyancy force in this case based on hydrostatic pressure, and that is rho g h. If h decreases, that means your pressure gradient decreases in horizontal direction. Okay, and that is why we will try to solve for this box type gravity current, and we will assume that originally this was the amount of fluid that was released, and after a certain time it becomes something like this, and after even longer time it becomes something like so. This is at t equal to 0, this is t equal to t1, t equal to t2. So it is going from t equal to 0 to t equal to t1, t equal to t2, and we will assume that this is the x-axis. So basically this is moving in x direction, this is z direction. Okay, and here this is the position xn, and we will call this as h. Okay, in this case now this is xn, here it is h, here again this is xn, and this is h. Okay, so xn here is the gravity current length, and in fact I should write xn as a function of time, and h here, which is also a function of time, is gravity current height, or you can also call it depth depending on how do you define it. And we see that xn increases with time, whereas h decreases with time, right? And that is why xn times h remains constant. Okay, xn increases, h decreases, and the total volume remains constant because we are assuming no mixing between the gravity current and the ambient fluid. Between the gravity current and ambient. Okay, and now because xn times h is constant, we can define that as initial volume. Xn times h is equal to a naught, that is the initial volume of the, or we can call it initial or released volume of the gravity current. This volume of the gravity current. Okay, and we solve it for a unit width in the third dimension. Let's say that is y. Okay, we are considering x-axis and z-axis as vertically upward, and there is y-axis that is into the paper or into the page here, and we consider that has width of 1, that is unit width. Okay, and that is why a naught is that basically represents the volume, and that is constant. All right, so now what we can do, we can define Reynolds number for the gravity current. In here we will use the height as the length scale, and so let's say u h over nu, where u is the gravity current velocity. Okay, and that is basically the speed with which this u is going. Okay, with which u, so u is basically a function of time. Okay, so u again I think put time term here. Ut is gravity current velocity, which decreases with time. Okay, so here we see that both u and h decrease with time, so we can define two regimes. Regime A, which is basically early time when your Reynolds number is much greater than 1. Okay, so when in the early time when your height is large and also velocity is large, so Reynolds number in the very beginning will be very large. Okay, and in this case when Reynolds number is much greater than 1, we can assume that your inertia force is much greater than the viscous force in the gravity current. Okay, and therefore initially the viscous force can be neglected, right? So that is regime 1 or early time behavior of the gravity current when gravity current has just started. And now we know that we are injecting a fixed volume of fluid, fixed volume of gravity current, so that cannot maintain the same velocity throughout the flow. It has to decrease because there is no additional force coming with the gravity current, right? Because height decreases, as we have discussed, that actually decreases the buoyancy force, and if buoyancy force is decreasing, which is basically the driving force for the gravity current, your velocity decreases, right? And that is why there is regime 2, let's call it regime B, which is late time behavior, where Reynolds number becomes much smaller than 1. Okay, so in early time we have Reynolds number much greater than 1 when velocity is large, height is large. At later time when velocity has decreased, it has become much smaller, and also your height has become much smaller. In that case your Reynolds number is very small. In that case, now inertia force is much smaller than the viscous force, and therefore we can neglect inertia force. Okay, in regime 2, in case 2. All right, so in now we can see in regime 1 we are neglecting viscous force, whereas in regime 2 we are neglecting inertia force. But there is one more force which is actually balancing these forces. So in case 1 we have inertia force significantly, whereas in case 2 we have significant viscous force. In both the cases there is one force, that is the buoyancy force, that is actually balancing these forces. So in both the regimes, buoyancy force works as the driving force for the gravity current, right? Because buoyancy force is coming because of the density difference, and density difference remains between the between the gravity current and the ambient. Okay, so now we will try to find uh, the different forms of these forces and how they relate with each other. So basically what we understand from here is, in regime A your buoyancy force is balanced by the inertia force, and in regime 2, regime B, buoyancy force is balanced by the viscous force. Okay, so this is what we know. In the early time inertia force is important, in late time viscous forces are important, but buoyancy force remains important throughout the flow, in the beginning as well as at late times, because the gravity current is flowing only because of the buoyancy force. Okay, so now we have to find these three forces, and we have to balance each other for regime A and regime B separately. So to find these forces, we will start with the Navier-Stokes equation. Okay, which we can write as du by dt, where we have rho term here, minus dp by dx plus mu d square u by dz square. Okay, and this Navier-Stokes equation is in x direction. Okay, because we are analyzing velocity in the x direction. That is our velocity of interest. In the viscous term, you can see we have only one one particular gradient, not the other ones, because this is the only dominant gradient here. So this one represents the inertia force, right, where d by dt is the material derivative. If you remember, that is something we have done, right, and this represents the pressure force or the buoyancy force, right, because buoyancy force here is coming because of hydrostatic pressure, and that is why dp by dx is same as the buoyancy force. In this one, the viscous force, which is significant only with respect to z, right, and this comes from boundary layer approximation or hydrostatic pressure assumption. That is something which again we have studied. I'll just make a note here, using hydrostatic pressure assumption, right, where we assume that gravity current length is much greater than the thickness, and that is why your variation of velocity only in z direction is important, not in other directions. Okay, and we are considering symmetric in y direction, so that again is not really a point of our interest. Okay, and all these forces here are per unit volume. All forces here are per unit volume. Okay, so now we can try to analyze, we can try to find each force one by one, because this is in derivative form and we have to convert that into a normal form. Okay, so let's start with F inertia. If inertia is basically, we are saying that these forces are per unit volume, so we have to integrate it for complete volume. So let's say for complete volume it will be rho du by dt dx dy dz. Let's consider a small elemental volume within the gravity current and say that for that small volume this is the force, and we have to integrate it for the complete volume, right? So that will give us the total inertia force that is there in the gravity current, right? And now we will apply by applying a scaling analysis, we can write that Fi, which Fi is simply the inertia force, we'll call it Fi, is proportional to rho u over t, and dx will be equal to xn, y will be w, and z will be equal to h. Okay, so we are assuming that your du is proportional to u minus 0, so that is equal to u, dt is proportional to delta t, that is simply equal to whatever the time we are analyzing, and your dx is proportional to xn, that is the total length of the domain. Dy is, let's say, w, that is the width in the y direction, and dz is proportional to h. Okay, so this is when we do scaling analysis, we consider this integral or derivative for complete domain, not for a small element. And for us, complete domain is the complete gravity current, and that is why we consider rho u times t xn w h. Okay, where h w here is the width in y direction. All right, and now here we can assume one more thing, that u also is equivalent to xn over time, right? U is velocity and xn is the length in which we are applying u, so that should simply be xn over time t. So if I, which is basically the inertia force, that becomes xn over t t xn h w. Okay, and this xn over h is something that we have already analyzed. So xn over h here is a naught, that is the initial volume that is released, right? And that is why we can call this as a naught, and that is why this will give fi to be proportional to rho xn a naught w over t square. Okay, that is the formula we get for fi, and that is the dimensional formula, or this is equivalent values, which is not numerically equal, and that's why we are using equivalent sign. So this is dimensionally consistent but not numerically. Okay, so we have found this one, and later we will see how to convert this into numerically consistent equation. So let's call it equation 1, that is inertia force, right? So we have got the inertia force. Now we will find the let's start with viscous force, or let's go one by one. So we can start with the buoyancy force. Buoyancy force, we will call it Fb. So Fb is equal to dp by dx, dx dy dz, and again this is integrated for the volume, right? Because we know that this force is per unit volume, and if you want that force for complete volume, you must integrate it for complete volume. Okay, so here again our dp here is basically we are considering the hydrostatic pressure, and in hydrostatic pressure, if let's say we have this gravity current which is moving this side, and it has the height h, and density here is rho naught, here it is rho a. So the flow is happening because of, let's say, p1 here and p2 here. So p1 here is rho naught gh, and p2 here is rho a gh. So delta p basically is equivalent to rho naught minus rho a gh, or delta p is equivalent to delta rho gh, right? So this is something we have, and that is why now when we convert this particular equation into dp by dx, we can write it as fb to be equivalent to delta rho gh over xn wh. Okay, and this again is coming from scaling analysis, right, where again in scaling analysis, instead of considering small element, we consider the complete flow domain. Okay, and based on that we try to find the equation where we convert that into equivalent sign, and later we'll convert that into equal sign by considering some prefactors. All right, so here we see that this xn cancels with the xn there, and we can write this as delta rho g h square w, and h square, if again we remember, uh, xn times h is equal to a naught, so a h is actually equal to a naught over xn. So we are trying to convert everything in form of uh, xn, and that is why we'll convert h back into xn. So this actually gives us ab times delta rho g. This will become a naught square w over xn square. And here we can do one more thing, that we multiply row to the top and to the bottom. So we write row over row, so we just multiplied row at the top and bottom, and now we can convert this into g prime, right? That is something we have used before, and that is the reduce gravity. Okay, so fb now becomes rho g prime a naught square over xn square w. Okay, this is the second equation that we got. So first one is there, that is F inertia, and this one is F buoyancy. So that is equation 2. And now we can go find the viscous force. Okay, so we have got the buoyancy force, we have got the inertia force, and now we will find viscous force, and we will write F mu as and now we will repeat the process that we did for others. So that is, this is integrated for volume, d square u over d z square dx dy dz, and there is a mu term, right? So again scaling analysis will give us mu u over h square xn w h. Okay, and that is why we are z is proportional to h, so we have written h here, and this will cancel with each other, and this will give us, if mu is proportional to mu, where u is again, so this becomes mu xn w over h, and u can be written as xn over t, right? That is something we have done before, and that is why this equation will convert into xn w over h xn over t, and that will give us f mu to be equal to mu. And another thing we can do here is we can use h as x naught over xn, right? These are two things that we have already used. So by converting this, we get mu xn cube over a naught t w. Okay, this is equation 3 we got. Okay, so far we have got this dimensionally uh, valid equation for inertia force, that is equation number 1. Then for buoyancy force, that is equation number 2. And then for viscous force, that is equation number 3. Okay, and now we are going to equate these different equations for different flow regimes, and we are going to find the formulas for the gravity current velocity, gravity current length, etc.